This is Official Nerd Business.
Hello nerd boys and girls, welcome back. Today we are going to take a look at Euler problem number 7. As usual, I've created a base template file which fits in the program that we've written for executing all of our solutions. And if you are not with the program, this can run perfectly fine on its own. Let's see, problem number 7 is concerned with the 10,001st prime. By listing the first 6 prime numbers we see that the 6th prime is 13. What is the 10,001st prime number? I've already declared a parameter with the default value. This brings us to a point that I wanted to discuss anyway, so I'm happy that this problem does this for us. We are able to check up to a certain number to see what primes are in the range from 0 to that number, but we could not use the sieve to extend the number until we have exactly 10,001 elements on our primes list. And a problem I had with the original sieve implementation, which is in lib Euler, if you open that, this sets up a list of Boolean values for every number from 0 up to whatever upper bound we provide. However, if that list would not reach 10,000 primes, then we would rerun this function with a new upper bound, and this would clear everything it had already done. It would clear everything that we already knew of all primes up to that number, and start all over again. And if we are going to take a couple of steps at solving this problem, say we start at 100,000, see if that has the numbers we need, then run up to 200,000, we would redo the entire range from 0 to 100,000. So I've been working on that. I made a little test file here where I copied in the original sieve function, and where I created a what I'd like to call a persistent sieve. So one that does not forget all the work it has done already, which not only takes in the array of prime numbers themselves. In the original sieve function we have a list of booleans, but we discard the list of booleans and convert it to a list of integers containing only those numbers that are prime. Only those numbers, in fact only the indexes of numbers of which the boolean value is true in the list of candidates. That's basically how the sieve works, if you recall. And what I did for this function, I created a module variable which will hold the list of booleans, Boolean primes register. It has double underscores out front to clearly indicate definitely don't use this outside of the module, and that's convention. In this function it imports that variable as a global as well as the primes list. And then it looks, it sets this variable to however high we've already gone before. This is 0 if the list is empty, otherwise it takes the length of the list. This is a failsafe for calling lang on an empty list. Python doesn't like calling the len function on a list that has only been declared as such and doesn't have any elements yet. So there's a failsafe for that. If whatever upper bound we provide to this function was already checked for, then we just return, and these two variables will hold all the data we need. If not, then we need to extend the Boolean prime register with, if it was currently empty, then we need to set our default values for 0, 1 and 2. And fill in the rest. This is the same bit of code that we have on the candidates list in the original Prime Sieve. And if we've already checked primes before, then we simply need to extend the list with assuming all the coming values are primes and marking off those that are not, for whatever bit we need extra from the previous upper bound to the new upper bound. Then we need to rerun all the primes. This is the integer prime list, so the list with exclusively primes. And we need to start at 2 and work our way through the new range, marking off all multiples of 2, marking off all multiples of 3, marking off etc, etc. That's what this bit of the code does. If we find a number, the first number that any prime will tick off is its own square. And if we find a prime number, and these are in ascending order, so if 5 times 5 is 25 exceeds whatever upper bound we give this, then there will be no more primes on this list that will mark off multiples in the new list, and we can exit this bit of code. This is another copy from our original sieve function, basically. Though it doesn't work on the candidates list anymore, it now works on the module variable. And then we, if we've checked off all the primes we previously had, or if this is the first time this function is called, then this bit of code kicks in with the same breakout condition. This is new, but all the rest is pretty much the same as in the original sieve code we had. And then also this bit where every prime in the new bit of the list that we find is also added in order to the integer primes list. To see if this is any faster than the original sieve function we had, we need to do a little test. So I've set up a bit of testing code starting here. This code is called whenever we run this file. I do 2 imports, one for random because I want to use random numbers in our coming test, and one for time because I want to be able to time the execution of our test code, obviously. Results, this is a little bit of storage where I will store my results in. I chose for this because during my initial test I also printed out the numbers we were currently testing, and I'll show why I chose this in a bit. The random values, will be a list containing 50 items. Those 50 items are chosen between 0 and 100,000. And I sort the list, so every consecutive call to either one of our prime sieves will have a new higher upper bound. For posterity's sake, I print the maximum and or minimum and maximum values of our randoms list. Then we test our original sieve. We reset the module variables to their empty values. We start the timer. Then we pick out every random value that we put on the list. This is the bit where I wanted to see personally how far my tests were coming along, and if I would have simply printed the test results in between them and sieve 2 started running, I would no longer see this and would no longer be able to have these right below each other on the screen. That's why I appended this string here that shows how well we did, what the results of this run were, and I do the same here and then print both results consecutively so they show up next to each other on the screen. So that runs the original sieve. Then we have exactly the same code except we call the other sieve function, so this should remember what it did and not rerun all tests on the previous prime numbers or on the previous numbers that we shove into here, because it's always ascending. It will only solve for the new bit, and then again store how well we did and then print that. So let's run it. Takes a couple of seconds for the first sieve to run. and it takes no time whatsoever for the second sieve to run. So here are the results. We searched first for all the primes up to 8010, and then we ran all the way up to 469,000. And our original function found 40,000 primes, of which the highest was very close to our upper bound here. And it took 3.5 seconds. Personally, I think running only 3.5 seconds over 50 consecutive calls to the sieve function with the highest run going all the way up to 500,000 is in fact not terribly bad. But not running the code over all of the things we've solved previously, we find that we get exactly the same results. So the code itself checks out. We find the same primes, we store them, we treat them exactly the same. So the list length is completely the same, and the highest element we found is the same. That tells me that everything in between is probably right. And it took us no more than 0.1 seconds. So this runs 35 times faster than this. I was quite astonished with the improvement that we got here. So I would say that we would copy our persistent sieve function into our lib Euler file. So I'm just grabbing the function. I am not copying the name of the function because I just simply want to replace everything we have here. The primes variable is already in here, but this bad boy isn't. So let's add that one as well. And if we were to test this on problem 5, for example, this uses the prime factors function, and the prime factors function again uses the sieve. So if we run our main code for problem number 5, then we get the correct output. So this seems to check out. Our replacing our sieve function worked according to plan, so that fixes us for the test file and the lib Euler file. Now for finding the 10,000th prime. Let's see how we go about that. We want to give a certain upper bound value to our sieve function, I guess. And let's start this out at, well, 10,000 would be a bad number because we would need 10,000 first, but we also know that not every number is a prime number, obviously. Can we assume, given what we just saw from the other function, we had 4 or almost 500,000 numbers checked and we found 41,000 primes? Can we say that for numbers in this order of magnitude, about 10% of the numbers is prime? I think that is a pretty decent assumption. So let's check for everything up to 100,000. Then we want to first we want to import our lib Euler. Then we want to call this. The underscore does indicate that this is an internal method. So we shouldn't be calling it directly. But we will for now. In the near future we will probably add some functions to our lib Euler that will make this slightly more user friendly. For now I think doing the code work on fixing the sieve for consecutive calls is all we want to do on the library and on the module, and for now we want to just solve Euler 7. Now let's check if the length of E primes. This only holds our prime number, so the this one we should definitely not use this one outside of the module code, and this runs all the way up to 100,000. This has 100,001 elements because we've also added 0, but this should only hold the prime numbers. And if the length of this list is greater than or equal to whatever n we got in here, in fact not if, but while this length is less than whatever we wanted, we want to increase our upper bound by 10,000. And rerun this. Now, the fix entails that if 100,000 doesn't contain the 10,000 in first prime, then this will run for 110,000, but will not recheck every number up to 100,000. So, quite a win there, I'd say. So let's rerun that until we do have a number, and then we want to return e.primes at position 10,001. This seems to check out. This is fine. I'd like to run program number 7 with the default input, please. And that is correct. We were slightly over 100,000, so our first guess was in fact pretty decent. It seems that our sieve was called only twice, and we ran this in 0.02 seconds, which is pretty quick. I'm pretty happy with how this turned out. As you can see, we still have a lot of work to do on our module, on designing everything in the Euler module to be very user-friendly for use in our actual solutions. But for now, I want to leave you with this. Don't forget that you can look up all of my source codes on the GitHub, link in the description, and I will see you next week. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.